Have you ever wondered how the magnetic field behaves around a circular coil? Today, we will derive the formula for the magnetic field at any point along the axis of a current-carrying loop, a fundamental concept in electromagnetism. To solve this, we rely on the Biot-Savart Law. This law allows us to calculate the infinitesimal magnetic field contribution, dB, from a tiny segment of the wire, dl, at a specific observation point in space. Let's define our geometry. We have a circular loop of radius r. We want to find the magnetic field at point P, located at a distance x from the center along the loop's central axis. Using the Pythagorean theorem, the distance r from the current element to point P is the square root of r squared plus x squared. This distance is constant for every element along the circular path. The magnetic field vector dB produced by a top element dl is perpendicular to the line connecting the element to point P. This vector can be resolved into two components, one along the axis and one perpendicular to it. Notice the symmetry. For every element on the loop, there is an opposite element. Their perpendicular components cancel each other out perfectly, meaning we only need to sum the components that lie along the central x-axis. The net magnetic field is the integral of the axial component, dB times cosine of phi. By looking at our geometry, we can see that cosine of phi is equal to the radius r divided by the distance r. We substitute our expressions for dB and cosine of phi into our axial equation. Since the current, radius, and distance x are constant for all elements on the loop, they can be pulled out of the integral. Now we integrate the element dl around the entire circle. The integral of dl is simply the circumference of the loop, which is 2 pi times the radius r. This covers every contributing segment of the wire. After simplifying the constants and pi terms, we arrive at the final expression for the magnetic field on the axis. This formula describes how the field strength changes as we move away from the center of the loop. Let's look at special cases. At the center of the loop, where x equals 0, the formula simplifies to the well-known expression, B equals mu naught times I, divided by 2r. This is where the field is strongest. When the distance x is much larger than the radius r, the field strength drops off following an inverse cube law. At these far distances, the loop begins to behave like a magnetic dipole. Let's try a calculation. With a current of 5 amps, a radius of 10 centimeters, and an axial distance of 20 centimeters, we can plug these values into our derived formula to find the exact magnetic flux density. First, we find the distance r, then calculate the denominator. By carefully applying the constants, we find a magnetic field of approximately 2.82 microteslas at this specific point along the axis. Visually, the field lines are straightest and most concentrated at the center of the axis. As you move away, they curve back around the wire, forming continuous closed loops as required by Gauss's law for magnetism. To summarize, symmetry cancels perpendicular field components, the field is strongest at the loop center, and it diminishes rapidly as you move along the axis. These principles are vital for designing solenoid coils and MRI machines. Quick question: if we double the radius of the loop while keeping the current the same, what happens to the field at the center? Since B is inversely proportional to R, the field strength would be halved. Thank you for learning with us. Generated by Vision Solve AI.